Welcome back to the Deep Dive. Today, we're venturing into, well, what's probably the most intense technological competition of our time, the global AI hardware arms race.
It really is.
We're looking at the future of infrastructure, the chips, the servers, the supercomputers, all the stuff that's powering generative AI and increasingly enterprise efficiency.
It's definitely more than just competition. It feels like an infrastructural gold rush. And it's driven by both massive enterprise demand and, frankly, some pretty fierce geopolitical tension.
Yeah.
The numbers alone signal the urgency here. I mean, look, the total global AI market, it was already valued at a pretty substantial $233.46 billion in 2024.
Which is already huge.
Right. But the projections show that figure multiplying almost 8 times.
Right.
It's expected to explode to something like $1.77 trillion by 2032.
Wow, $1.77 trillion. That kind of growth trajectory, it suggests a really fundamental reshaping of the global economy is happening right now. And if we zero in just on the physical foundation, the hardware itself, that market is expected to jump from, about $59.3 billion this year?
Yeah, roughly that.
To nearly $300 billion. The figure is $296.3 billion by 2034.
And that sustained high-speed growth, you're talking a compound annual growth rate, a CAGR, of 18% just for hardware and over 29% for the overall AI market. It just shows we are in a massive, prolonged build-out phase.
Definitely.
And what makes this deep dive so critical, I think, is understanding the defining conflict here. On one side, you've got the established Western technological supremacy, anchored by NVIDIA and the enormous hyperscalers, Microsoft, Amazon, Google.
The incumbents. And on the other side, you have the challenger, China's relentless state-backed push for AI sovereignty, and that's really spearheaded by Huawei.
Exactly.
And the narrative here is just fascinating because due to those external constraints, the export controls, Huawei can't simply match the raw individual speed of the best chips in the world, right?
Precisely. They just don't have access to the most advanced manufacturing molds right now, so they're forced to adopt a completely alternative strategy.
Which is?
It's basically about scaling up their computing clusters to absolutely unprecedented levels. They're using clever system-level architecture to try and overcome those persistent limitations in raw semiconductor manufacturing power.
So it's a direct clash. Raw silicon power versus massive systemic engineering scale.
That's a good way to put it.
Understanding which approach wins out or how they coexist and where all that corporate spending is going to concentrate over the next, say, decade, that's absolutely crucial for you, the listener, to grasp.
Okay.
Let's start by unpacking where the immediate money is flowing right now. We seem to be in a phase where the biggest tech providers are under, intense pressure to deliver actual concrete return on investment ROI.
Oh, definitely.
Enterprise customers are demanding optimized performance, sure, but also profitability and security from these AI systems they're investing so heavily in.
Yep. And we've kind of distilled 5 key trends that seem to define this market shift based on what enterprises are asking for.
Great. What's the first one?
The first, and arguably the most power-hungry trend, is the escalating demand driven by AI reasoning.
Okay, reasoning. What does that mean beyond what we've seen with things like ChatGPT?
Well, we're moving past that initial wave of generative AI, which was amazing, but often excelled at relatively simpler tasks like summarization or basic classification,
Well,
AI reasoning requires more advanced cognitive functions, think sophisticated decision-making, recognizing subtle patterns in really complex data sets, advanced learning capabilities.
right. So if the AI is going to make important, maybe even high-stakes decisions autonomously, that capability is going to need an astronomical amount of computing power.
Absolutely astronomical. We're talking about a colossal spike in compute demand that hits every single stage of the AI lifecycle.
Every stage.
Yeah, the initial pre-training of those huge foundational models, then the post-training fine-tuning to specialize them, and, crucially, the constant inference cycles where the AI is actually doing its job, making those decisions in real time.
Okay.
This complex reasoning. It's the engine driving this relentless demand for ever more powerful semiconductors and chips.
And that very need for optimized performance, it leads directly into the second trend you identified. The rise of custom silicon and this ASIC versus GPU debate.
Exactly. The hyperscalers, the big cloud providers, they're no longer content just buying off-the-shelf components from, say, NVIDIA.
They want more control.
They want more control and they want optimization. They're designing their own tailored data center architecture, focusing especially on traditional bottlenecks like memory bandwidth and power efficiency.
Right.
And this forces a core strategic choice for them. Do they stick with general-purpose graphics processing units, GPUs, which offer incredible flexibility for lots of different tasks?
Like NVIDIA's bread and butter.
Precisely. Or do they shift towards application-specific integrated circuits, ASICs?
And ASICs are.
Different how?
ASICs basically sacrifice all that flexibility. They're designed to do one single specialized task extremely well. But in return for losing flexibility, they deliver dramatically higher efficiency and performance for that one specific job, like running inference really, really fast.
Okay, so hyper-specialized. And we're seeing this shift accelerate already, aren't we? With Google's TPUs, Amazon's Trainium, and Inferentia chips.
Definitely. And executives we've looked at are noting that this demand for custom silicon is likely to explode even further with the adoption of edge AI.
Putting the AI processing right onto the devices themselves.
Exactly. Putting low-latency AI processing right onto your phone or into factory sensors or cars, that needs specialized, efficient chips, often ASICs or NPUs.
Got it. Okay, trend number 3 takes us into the economics you mentioned. Yeah, this is about the underlying economic mechanism. Cloud migrations and hyperscaler revenue. It's pretty straightforward in one sense. The major cloud providers are investing hundreds of billions into commercial servers, expanding their AI offerings constantly.
And their goal is basically ecosystem lock-in, right?
Totally. Get enterprises to rely on their entire software stack, not just the compute. That maximizes platform stickiness, market share, the whole deal.
But wait a second. If these tech companies, especially with custom silicon, are offering more efficient computing, shouldn't that mean businesses need to buy less raw compute power over time? It feels counterintuitive that improved efficiency would lead to higher overall spending.
Yes. That's the fascinating insight of the Jevons paradox, and it's such a critical economic driver in this whole hardware race. You're right, recent AI advancements genuinely improve computing efficiency. They lower the cost per calculation.
Okay.
However, the paradox, observed way back in the 1800s with coal, states that the resulting reduced cost makes the service so much cheaper and more accessible.
That people just use way more of it.
Exactly. Companies and consumers use it far more often or find brand new applications they couldn't afford before.
So improved efficiency doesn't actually reduce overall consumption. It increases it, potentially exponentially.
Precisely. The lowered barrier to entry results in higher overall consumption of AI services. This fuels perpetual long-term demand for the entire ecosystem, the hardware, the software, the services.
Wow.
And strategically, this means the hyperscaler who can reduce the cost of compute the fastest potentially gains a massive long-term advantage. It forces competitors, like NVIDIA, to constantly accelerate their own chip roadmaps just to keep up on that price-performance curve.
That efficiency consumption feedback loop is massive. Okay, trend 4 seems to bring us back to accountability, systems to measure AI efficacy.
Right. As AI becomes absolutely essential for business operations, companies need hard proof that these huge investments are actually generating a positive ROI. You can't just spend billions on faith.
They need to show it works and pays for itself.
Exactly. And this has created a boom in tools focusing on observability and evaluation.
Observability
means having the insight to understand exactly how a complex AI system is behaving internally and why it made a specific decision or prediction. It's about peering inside the black box.
Right.
As one executive source put it quite well. Writing code has become much faster with AI, but now the value is in testing and understanding it and seeing if it works for the business.
The complexity of these systems means you can't just trust the output blindly. You have to be able to verify the process, especially for regulated industries.
Precisely. And that verification requires data management on a whole new scale. This is fueling what some are calling the data lakehouse revolution.
Cows. Okay, break that down.
Think of it this way. A traditional data lake is like a giant, cheap, but kind of disorganized storage space, like a garage filled with everything. A traditional data warehouse, on the other hand, is like an expensive, highly structured library, easy to find things, but costly and less flexible. The data lakehouse tries to unify them. It offers the low-cost, massive storage of the lake, but adds the structure and management features of a warehouse on top.
Best of both worlds.
That's the idea. And this unified platform is becoming necessary to properly feed and manage the data for the best-of-breed AI services that modern enterprises are demanding.
Makes sense. All right, finally, trend 5. This sounds like the really futuristic one. Building an agentic AI future.
Yeah, this is the long-term goal that, if realized, promises to radically change how businesses operate.
Agentic AI, what does that entail?
Agentic AI moves beyond AI as just a tool that humans use. It involves deploying large systems of AI agents, think autonomous software programs that can observe an environment, make independent decisions, take actions in the digital or even physical world, and adapt to changing conditions, all with minimal human intervention.
Wow, so autonomous AI workers, essentially.
In a sense, the long-term vision is things like truly personalized content and shopping assistants that are intimately familiar with your preferences and needs, maybe running entire business processes in the background autonomously.
That sounds like a dream for productivity, efficiency.
Hmm.
Maybe a bit scary, too. But if this is the inevitable future, why are the executives we're hearing from cautioning against expecting an immediate payoff?
They seem very worried about the classic hype cycle. While the foundational infrastructure, the hardware we're talking about, is being built now, true enterprise-wide profitability from fully agentic AI systems, that's probably not expected for another 3 to 5 years, maybe longer.
What are the current bottlenecks holding it back?
The limitations right now are pretty profound. Think about the cost and, critically, the security risks involved in granting AI agents autonomous access to sensitive enterprise systems and data. That's enormous.
Yeah, letting an AI loose in your company systems.
Exactly. Plus, you need extremely robust and large memory architectures to support the complex, multi-step reasoning these agents would need to perform. And the training costs for these advanced decision-making models, they remain prohibitively high for most companies today. The payoff is likely coming, but patience and a lot more development is definitely required.
Okay, that gives us a great handle on the strategic why the enterprise demands shaping the market. Now let's dive into the core hardware battleground itself, Section 2, and look at what specific pieces of metal and silicon are actually being bought and sold right now to deliver that ROI and, drive that massive consumption we talked about.
Right. So if we look at market leadership and how the processor market is segmented in 2024, the clear incumbent champion is still the graphics processing unit, the GPU.
NVIDIA's territory.
Absolutely. GPUs hold approximately 39% of the market share. They really dominate cloud hardware primarily because their parallel processing power is just unmatched for training those massive foundational AI models.
But you mentioned growth earlier. The fastest growth by far seems to be happening elsewhere in the processor landscape.
That's right. That would be the neural processing unit, or NPU. These are projected to grow at a CAGR of over 19%.
Wow, faster than the overall hardware market. What's driving that specifically?
It's driven almost entirely by the big shift toward on-device AI, moving the inference part, the actual using of the AI model, away from centralized cloud data centers and onto the devices themselves.
Like smartphones, laptops.
Exactly. Smartphones, laptops, smart vehicles, factory robots, you name it. NPUs, which you see in platforms like Qualcomm's Snapdragon, for instance, are essential for delivering a low-latency, energy-efficient inference right at the edge where the data is generated or needed.
And the benefits are?
Well, it improves speed, no round trip to the cloud. It enhances privacy because sensitive data might not need to leave the device. And importantly, it relieves some of the immense pressure on those giant, power-hungry data centers.
So we've got GPUs dominating the centralized training in the cloud, and NPUs emerging as key for the decentralized future of AI consumption at the edge. What about the crucial support system, specifically memory? You touched on this earlier.
Yeah, the demands of generative AI, especially large language models or LLMs, have made memory architecture more critical than ever before. And high bandwidth memory, or HBM, is the undisputed king here right now.
HBM, how dominant is it?
HBM accounted for a massive 47% of the entire memory and storage market share related to AI in 2024. And it's projected to grow at a CI of over 19%, mirroring the NPU growth.
Okay, why is HBM so critical for these LLMs? What problem does it solve?
LLMs require just enormous amounts of parallel data processing. Think about it. They're constantly moving billions, sometimes trillions, of parameters back and forth between the processing units and memory during both training and inference.
Right.
Standard memory, like the DDR RAM in your PC, simply can't feed data to these powerful GPUs fast enough. It creates a serious computational bottleneck. The GPU is sitting there waiting for data.
Yeah, got it. And HBM solves this how?
HBM uses an innovative approach. It stacks memory chips vertically, often right on the same package as the GPU, dramatically shortening the physical distance the data has to travel.
Less travel time.
Exactly. This massively increases the data transfer speed, the bandwidth, and minimizes latency. That's why it's essential for keeping those power-hungry AI processors fed. And it's why companies are racing to innovate here, like Micron, for example, launching their next-gen HBM4 36GB chips next year.
It feels like the moment generative AI really broke into the public consciousness, particularly with ChatGPT, it just poured gasoline on all these hardware trends.
Oh, absolutely. You can draw a clear line.
Yeah.
The speed of adoption for ChatGPT was just a global wake-up call for every industry.
What were the numbers again?
It reached 1 million users in just 5 days. 5 days. If you compare that to other huge platforms like Netflix or Facebook, they took years to reach similar milestones.
Right.
That incredibly rapid acceptance forced basically every business on Earth to immediately accelerate their AI investment plans, realizing this wasn't some niche academic thing anymore.
And the practical applications for these LLMs within enterprises are now becoming truly transformational, aren't they? Not just like incremental improvements.
They really are. We're seeing vast utility in areas like customer support chatbots, sophisticated internal knowledge retrieval systems, automated content generation. But perhaps the most impactful metric we're tracking is in coding automation.
Helping software developers.
Massively. Some estimates suggest that AI-powered coding tools are increasing a software engineer's output by potentially tenfold or even more. Just think about the productivity gains across that entire sector alone.
That's huge.
And beyond that, you have specialized industries benefiting enormously. Biotechnology, for instance, is using AI to accelerate clinical trial analysis and navigate incredibly complex regulatory submissions. The legal sector is increasingly using AI for paralegal work, automating things like document review, research, and contract analysis.
So the demand is clearly exploding across the board. Now, who are the main players actually selling all this high-tech equipment? It sounds like a pretty concentrated market.
It is intensely concentrated. The top 7 players, and this list won't surprise many, NVIDIA, Microsoft, Qualcomm, AWS, Intel, AMD, and Apple, together they controlled something like 83% of the AI hardware market as of 2024.
And NVIDIA is still leading the pack.
Unquestionably. NVIDIA remains the uncontested leader, specifically in the AI chip market, holding roughly 50% share globally. But their dominance isn't just about the raw power of their GPUs, like the H100 or the new Blackwell series.
What else is key to their dominance?
It's the near-ubiquitous adoption and maturity of their CUDA software ecosystem.
Right, CUDA. Explain the strategic advantage there. Why is it so powerful for NVIDIA beyond just being software?
Okay, so CUDA isn't a chip itself. It's the parallel programming model and the whole software stack, libraries, compilers, tools that developers use to actually unlock and harness the massive parallel processing power of NVIDIA's GPUs. And it's been developed and refined for over a decade now. Millions of developers know it, they trust it, there's a huge amount of documentation and community support. Crucially, the entire AI research and development ecosystem, the academic papers, the open source libraries like PyTorch and TensorFlow, the pre-trained models is largely built around CUDA.
So it creates inertia.
It creates powerful lock-in. When an AI startup or even a large enterprise chooses a hardware platform, adopting CUDA is often the path of least resistance. It's incredibly expensive and complex, both in terms of time and engineering resources, for a company heavily invested in CUDA to switch to a competing hardware architecture, even if that competitor theoretically offers a slightly faster or cheaper chip on paper.
So the hyperscalers like Microsoft, AWS, Google, when they're fighting NVIDIA, they aren't just trying to build faster chips. They're fundamentally fighting to build a viable competing software ecosystem as well.
That's exactly right. And it's a huge undertaking. That's why they are investing absolutely astronomical sums in developing their own custom silicon. Think Microsoft's Azure Maya, AWS's Trainium and Inferentia chips, Google's TPUs.
And their motivation is twofold, you said earlier?
Yeah, twofold. First, obviously, to reduce their crushing reliance and, frankly, expense on a single third-party supplier, NVIDIA. And second, to deeply optimize their cloud services for both performance and cost, tailored specifically to their own infrastructure and software stack.
The Google's TPUs being designed from day one for machine learning.
Exactly. Google's TPUs were designed from the ground up specifically for accelerating neural network training and inference within Google's ecosystem. AWS's chips, like Trainium for training and Inferentia for inference, are similarly optimized to run as efficiently as possible within the AWS cloud environment, potentially offering better price performance for AWS customers.
And that level of investment is just staggering. We're not just talking about chip design, we're talking about massive physical infrastructure projects.
We absolutely are. Just consider AWS's Project Rainier, that's reportedly a commitment of something like $100 billion?
$100 billion.
100 billion into building purpose-built AI data center clusters designed around their own proprietary chips.
Yep.
This isn't just about buying some better servers off the shelf. It's a multi-year, decade-long effort to build a completely foundational infrastructure that allows them to control the cost, the performance, and crucially, the future trajectory of their AI cloud offerings. It's about securing their position as the essential utility provider for enterprises in the AI era.
Okay, so if that's the intense battle for optimization and market share among the established players, the fight for technological self-determination really defines our next section. We need to turn now to Section 3, the geopolitical showdown. And specifically, let's focus on Huawei's strategic response, given that they've been largely cut off from accessing those cutting-edge Western components.
Right. And the context here is absolute. You can't overstate it. Due to those ongoing U.S. export controls, China is locked in this national race for technological self-sufficiency, what they often term AI sovereignty.
They need to build their own.
They have to build their own. And Huawei, being a national champion, is at the forefront. But they openly acknowledge the fundamental problem. Their domestic semiconductor manufacturing capabilities, primarily through SMEC, will, for the foreseeable future, lag significantly behind the global leaders like TSMC.
So they simply cannot produce individual chips right now that match the raw performance and speed of, say, an NVIDIA H100 or the upcoming Blackwell chips.
Correct. Not on a node-to-node comparison. So if they can't win purely on the raw speed of a single chip, their entire strategy has to pivot.
And that pivot is towards.
It's become a masterclass, really, in system-level engineering and architectural innovation. Their core strategy is, we will use significantly more of our domestically produced chips, maybe chips that are individually less powerful, but we will develop a superior networking architecture to make them all function together, almost perfectly, as one single, massive, distributed machine.
So it's a philosophy of achieving performance through sheer scale and interconnect efficiency, rather than just raw silicon speed from one chip.
Exactly. Scale and architecture over raw speed. This involves constructing what they call superpods. Think of a superpod as a single logical computing unit composed of potentially thousands of physical processors and then coordinating groups of these superpods into even larger superclusters.
Okay, let's try and examine this ambition through their public Ascend chip roadmap. It sounds like they're not planning slow, incremental upgrades here. The cadence seems quite aggressive.
That's right. To try and close that performance gap, Huawei is planning a very rapid one-year release cycle for its Ascend AI processors, aiming to effectively double the compute power with each new generation. It's incredibly ambitious.
Right.
The first major phase we're seeing details on centers around the Ascend 950 series, which is planned for launch across 2026. And this is where you can really see those geopolitical constraints becoming visible right in the hardware design itself, particularly around the memory interface.
How does the memory design reflect the geopolitical challenge?
Well, because they likely face ongoing restrictions on sourcing the most advanced high-bandwidth memory HBM components from international suppliers like SK Hynix or Micron.
They have to make their own version.
They've had to develop their own proprietary HBM packages and interconnect standards. And interestingly, they're tailoring chips with different memory subsystems optimized for different stages of the AI workflow.
Okay, like what?
So within the 950 series, they have the Ascend 950 PR. The PR likely stands for prefill recommendation. This version seems optimized for compute-intensive tasks, like maybe prefilling the context window in a large language model, and it uses a proprietary, possibly lower-cost HBM called HiBL 1.0. That's slated for early 2026.
Okay. And the other version?
The other, and perhaps the more critical model for large-scale training, is the Ascend 950 DT. DT is likely for decode training. This one is optimized heavily for memory bandwidth, crucial for training and running inference on large models. It uses their more advanced HiZQ 2.0 HBM standard, which reportedly delivers a really impressive 144 gigabytes of memory capacity per chip and a massive 4 terabytes per second of bandwidth. That's due Q4 2026.
That dual-pronged approach, tailoring memory for the task, seems designed to maximize the use of domestic components while still trying to hit pretty high-performance targets. What are they aiming for with the 950 series?
They're targeting 1 petaflop PS of performance and FP8 precision, that's a standard format for AI calculations, and 2 petaflop PS in FP4, which is an even lower precision format that can accelerate things further.
Okay, 1 to 2 petaflop PS per chip. And they're already planning the next 2 generations beyond that.
Yes, the roadmap extends out. The Ascend 960, slated for late 2027, aims to roughly double the compute power, the memory capacity, and the memory bandwidth compared to the 950 series. Interestingly, it's also expected to support a new proprietary data format called HiFEF4, which likely aims to get more precision out of 4-bit calculations than standard FP4 formats. The target there is pushing towards 4 PFLOPS in FP4 per chip.
Doubling again.
And then looking even further out to Q4 2028, they have the Ascend 970 on the roadmap. The goal there is another doubling, aiming to double the FP4 and FP8 compute performance and the memory access bandwidth compared to the 960. That takes the per-chip target to around 8 PFLOPS in FP4.
Doubling performance every year?
Yeah.
That's incredibly aggressive. But you said the real technological linchpin, the thing that makes this whole scale overspeed strategy even remotely feasible, isn't just the chips themselves, it's the networking infrastructure connecting them.
Absolutely critical. That brings us to their Unified Bus 2.0 UB interconnect technology.
Okay.
This technology is potentially groundbreaking because it's specifically designed to overcome the monumental challenge of latency, the delay when you're trying to coordinate tens of thousands or eventually maybe even a million relatively slower chips to work together as one.
So Unified Bus 2.0 is designed to make, 10,000 plus NPUs behave as if they are a single monolithic computer?
That's the core design goal, yes.
Yeah.
To make the distributed system act like one giant unified processor.
What was the specific engineering breakthrough that enables this? What makes UB 2.0 special?
Well, traditionally, when you try to network thousands of chips together over longer distances within a data center, you often face a trade-off. You can use copper wiring, which is reliable but struggles with signal integrity over distance, or you can use optical fiber, which can go much further but introduces complexity and potentially higher latency at the connection points.
Right.
What Huawei claims to have achieved with UB 2.0 is effectively combining the reliability of copper signaling with the long-range capability of optical interconnects. This allows the unified signal to travel reliably over 200 meters within the data center fabric.
200 meters is quite far in a data center context.
It is, and crucially, they claim to do this while maintaining terabyte per second levels of bandwidth and minimizing signal degradation or delay.
And the latency figures, the delay, that's where the real performance lives or dies in a system this big, right? We heard the number 2.1 microseconds mentioned in the reports. Why is that specific number considered such a huge achievement?
Okay, yeah, 2.1 microseconds might sound incredibly fast, but in the world of high-performance computing and interconnects, gains of even 0.1 microseconds, a tenth of a microsecond, are fiercely fought over and incredibly hard to achieve.
Right.
Because when you have a massive cluster, let's imagine 10,000 chips all working on parts of the same problem. Each tiny step or instruction often has to wait for data or signals from other chips. That tiny delay, even just 2.1 microseconds, gets compounded across thousands of processors and thousands of communication steps.
So minimizing that delay is paramount.
Absolutely paramount. Achieving such ultra-low latency, if they've really done it consistently at scale, means that even though the individual Ascend chips might be slower clock for clock than, say, an NVIDIA chip, the system can pass information between them so incredibly rapidly that the overall cluster acts much more cohesively and efficiently. It helps mask the performance deficit of the individual chips.
That makes the system architecturally potentially superior, even with slower components. But doesn't scaling to this level, connecting tens of thousands or even a million chips, introduce enormous risks? I mean, coordinating that many parts sounds like a logistical and engineering nightmare. Is there a danger that this relentless pursuit of scale drives unnecessary complexity or increases the chances of system failure?
That is absolutely the core strategic risk Huawei is taking here. They are essentially betting the farm that the constraints on accessing leading-edge process nodes will persist for them, forcing everyone eventually toward these kinds of massive scalable architectures to get more performance.
So they're trying to get ahead of that curve.
Exactly. But you're right, the challenges are immense. Managing the sheer complexity, the power consumption, the cooling requirements, and ensuring fault tolerance across clusters of this unprecedented size. These introduce massive engineering hurdles. If even a tiny percentage of those, say, million chips fail or experience errors, the performance of the entire supercluster could be significantly degraded or even jeopardized.
How are they trying to mitigate that risk?
One key part of their strategy, which is interesting, is that Huawei is actively trying to foster an open ecosystem around this. They've released the technical specifications for Unified Bus 2.0 publicly. The hope is likely to encourage partners within China and potentially beyond, to adopt the standard, develop compatible hardware, and essentially share the burden of development, validation, and building out the software ecosystem around it.
Okay, let's talk about the culmination of this whole strategy.
Yeah.
The Atlas supercomputing clusters.
Yeah.
The scale here sounds genuinely astronomical.
It is absolutely astronomical. The first big milestone is the Atlas 950 SuperPod, which they expect to have operational in late 2026. This will use up to 8,192 of those Ascend 950 DT chips we discussed earlier, the one optimized for bandwidth.
8,192 chips in one logical unit. What kind of power does that represent?
That single logical SuperPod is projected to deliver 16 exaflop PS of peak performance and FP4 precision.
Okay, exaflop PS, remind us what that means.
An exaflop is 1 quintillion, that's a billion floating point operations per second. It's an incredible amount of compute power. To put it in perspective, that's the kind of power needed to potentially model the entire global climate system in high resolution in real time, or simulate extremely complex molecular interactions for drug discovery.
And how does Huawei claim this compares to what competitors are planning?
Huawei claims the single Atlas 950 SuperPod will offer something like 6.7 times more raw computing power than NVIDIA's planned NVL144 system, which connects 144 Blackwell GPUs. Now, that's likely a peak FP4 comparison, and real-world performance depends hugely on software and workload, but it highlights the scale difference. They also point out it uses 56.8 times more individual NPUs than the NVIDIA system.
Just packing them in. And then they plan to integrate these superpods into something even larger.
That's the next step, the true world-altering machine they're aiming for. The Atlas 960 supercluster, which is planned for late 2027.
Supercluster, what scale are we talking about here?
This system is designed to integrate over 1 million Ascend NPUs, presumably the Ascend 960 generation by then.
Over 1 million processors.
Yeah.
Working as one.
Working as one, connected by that unified SIM-to-bus fabric. The projected peak performance is 2 Zetaflop PS in FP8 precision and 4 Zetaflop PS in FP4.
Zetaflop PS. Okay, we went from Peta to Exa, now Zeta. That's the next frontier, right?
That is absolutely the next major frontier in supercomputing Z-scale. To try and put 4 Zetaflop PS into perspective, it's roughly 4,000 times more powerful than the world's fastest supercomputer from just a few years ago. It's almost difficult to comprehend.
And how does this compare to other massive AI clusters being built, like the one Elon Musk's xAI is reportedly building?
Well, Huawei projects that this Atlas 960 supercluster will significantly outstrip xAI's planned Colossus supercomputer, which is itself expected to be the world's largest cluster when completed, by utilizing roughly 2.5 times more individual processing units. Again, direct comparison is tricky, but it confirms their strategic goal is not merely to compete within China, but to attempt to redefine global leadership at the absolute highest end of system-level computing scale.
So this incredibly intense hardware race is happening simultaneously right across the globe. Yeah. Let's shift focus now in Section 4 to look at the broader picture. Global investment trends and the ongoing geopolitical challenges. Starting with the regional breakdown, where is most of this money actually landing right now?
Okay. North America, primarily the U.S., remains the dominant market leader by share. It captured nearly 33%, 32.93% of the overall global AI market share in 2024.
And within North America?
The U.S. alone drives something like 91% of that North American AI hardware revenue. This is overwhelmingly fueled by those massive hyperscaler investments we discussed, AWS, Google Cloud, Microsoft Azure, and anticipated huge buildouts like the Microsoft OpenAI Stargate project, which could end up being one of the largest private infrastructure projects ever conceived, potentially costing $100 billion itself.
Just incredible sums. However, you mentioned earlier that the velocity of growth, the speed, seems to be shifting eastward.
That's definitely the case. The Asia-Pacific region is by far the fastest-growing market overall. Hardware CAGR there is projected around 20%, but the overall AI market CAGR is closer to 35%, 34.70%.
Wow. What's driving that incredible pace in APAC?
It's largely driven by strong national AI strategies and, crucially, government-backed semiconductor self-sufficiency programs, particularly in China, but also increasingly in South Korea and India.
India, too.
Yes. India, for example, recently committed $1.24 billion over 5 years, specifically to its India AI mission, a significant portion of which is earmarked just for developing domestic semiconductor design and manufacturing infrastructure. They see this as critical national infrastructure now.
And what about Europe? Where does it fit in? Is it managing to keep up, or is it positioning itself differently?
Europe is currently the third largest market. Its growth is significantly driven by a slightly different emphasis, where the explicit political and economic need for sovereign AI infrastructure.
Sovereign AI, meaning keeping data and processing local.
Exactly. There's a strong push to ensure that European data is processed on European soil, subject to EU regulations like GDPR. This is backed by large-scale policies like the reported $225 billion AI Continent Action Plan, which aims to deploy AI chips and infrastructure across various key EU sectors, from industry to healthcare, while maintaining that data sovereignty.
Okay, circling back specifically to China for a moment. We talked about the future roadmap with the Ascend 950 and 960, but what about right now? The Ascend 910C is their current flagship alternative to restricted NVIDIA chips in that constrained market. How successful is it proving to be in practice?
The Ascend 910C is undoubtedly a major domestic achievement for China's semiconductor industry, particularly because it utilizes SMIC's relatively advanced 7-nanometer N+2 manufacturing process. That was a big step.
And how does it compare performance-wise to, say, the NVIDIA H100 it's meant to replace?
It's a mixed picture. Interestingly, the 910C actually boasts superior on-package memory compared to the H100. It has 128 gigabytes of HBM3 memory versus the H100's 80 gigabytes. That's a win.
But raw compute.
In raw compute performance, particularly for certain types of AI workloads, it generally trails the H100. Some independent analysis suggests the 910C delivers roughly 60% of the H100's inference performance for certain popular large language models, like DeepSeek R1.
Okay, so it's not quite a one-to-one replacement in terms of peak performance, but is it good enough? Is it sufficiently powerful to function as a viable, domestically manufactured, and crucially unrestricted alternative for Chinese companies?
Critically, yes,
Yeah.
that seems to be the consensus. While it might not match the absolute peak performance, its availability is foundational for major Chinese tech giants like Baidu, Tencent, Alibaba, and ByteDance. It allows them to continue powering their massive, expanding AI services and research efforts without depending on external, potentially sanctioned technology. It guarantees a degree of operational stability and predictability in a highly uncertain geopolitical environment.
Right. It secures their domestic supply chain for this critical component. Now, despite all this money pouring in and all this ambition, what are the primary challenges or restraints that are holding back even faster growth in the global AI hardware market?
While geopolitics itself remains a massive restraint, perhaps the biggest one. These reciprocal tariffs, for example, U.S. duties on Chinese AI chips and related components, and the potential for Chinese retaliation on other goods directly raise the production costs for essential hardware like GPUs, servers, FPGAs, and even cooling systems.
And that complicates supply chains.
Massively. It complicates global sourcing, forces companies to spend money redesigning and diversifying their supply chains, adds uncertainty, and ultimately those increased costs tend to get passed down, increasing consumer prices for the end AI-enabled services and products.
Makes sense. But are there also equally complex restraints arising from the technology itself? You mentioned things like the talent shortage and maybe the inherent opaqueness of these systems earlier.
Absolutely. Those are huge factors, too. The global lack of specialized AI talent, not just core AI researchers, but also the engineers needed to build and deploy these systems, prompt engineers, data scientists, AI ethicists, is genuinely hindering rapid deployment and innovation across many sectors.
And the opaqueness, the black box issue.
Yes, the black box effect remains a fundamental challenge, especially for enterprise adoption. This refers to the fact that many powerful AI algorithms, particularly deep learning models, produce incredibly accurate results. But their internal decision-making processes are so complex that the outputs are not easily verifiable or explainable, even by the experts who built them.
Man, hang on. If enterprises are demanding clear ROI and accountability, like we discussed in Trend 4, how can they possibly justify spending billions of dollars on systems they literally can't fully explain or verify? Doesn't the black box effect clash directly with that core demand for transparency and profitability?
It creates an enormous tension. You've hit on a key problem. It fosters significant user mistrust. Can I rely on this decision if I don't know how it was made? And it creates huge legal and regulatory exposure, especially in sensitive areas like finance, healthcare, and hiring. This is precisely why developing explainable AI, XAI models, and those accountability tools like observability platforms has become such a huge trend and area of investment in itself. Companies are being forced to invest heavily in making their AI systems more transparent to gain user trust and satisfy regulators. If a bank uses an AI to approve or deny a loan, they must be able to explain the reasoning behind that decision. A black box system fundamentally undermines that necessary accountability.
Okay, so it's a major hurdle they're actively trying to overcome. Despite these hurdles, though, one massive opportunity that's emerging is the rise of supercomputing as a service. What's that about?
This is becoming a really lucrative market, particularly for the hardware vendors and the hyperscalers. Essentially, the big cloud providers like Microsoft Azure, IBM Cloud, Google Cloud, and even Meta are now offering access to their incredibly powerful, high-precision supercomputer infrastructure, often powered by clusters of NVIDIA's A100 or H100 GPUs as a rentable public cloud utility.
So you don't have to buy the supercomputer yourself.
Exactly. This allows smaller enterprises, research labs, or even startups who could never dream of affording to build and maintain their own multi-million or billion-dollar supercomputer cluster to lease immense computing power on demand, often by the hour.
And the impact.
It dramatically lowers the barrier to entry for high-end AI development, rapidly accelerating the ability of many more organizations to train extremely complex models, run massive simulations, and deploy sophisticated AI applications without the enormous upfront capital expenditure.
Okay, that makes sense. Finally, let's look at the implementation breakdown from the reports. Where is AI adoption actually landing fastest right now, broken down by industry and by business function?
All right. The industry sector that currently dominates the market share in 2024 is BFSI, that's banking, financial services, and insurance. They hold about 18.90% of the market.
Why are they leading?
It's largely driven by the urgent, high-value needs in that sector for things like real-time fraud detection, complex algorithmic trading, sophisticated risk management modeling, and delivering highly personalized financial advice and services. In some regions, the impact is expected to be huge. AI penetration in banking alone is projected to add potentially over 13% to the local GDP by 2030 in some estimates.
Wow, okay, so BFSI leads in current share. Which sector is seeing the most explosive growth rate?
That would be healthcare. It has the highest projected CAGR, estimated at around 36.50%.
And the applications driving that in healthcare.
AI is being used in truly revolutionary ways there. Think advanced diagnostic imaging analysis, spotting things in scans humans might miss, analyzing complex genomic data for personalized medicine, drug discovery simulation, and even real-time patient monitoring. For instance, there are AI systems being deployed now that can monitor patients who are self-administering critical medicine, like insulin, and can actually detect potential errors in dosage or timing that humans frequently miss.
Incredible potential there. Okay, and if we slice it differently, looking at the business functions that are benefiting most from AI adoption.
The function leading in current market share, around 21.20%, is service operation. This is all about using AI to enhance customer service, think intelligent chatbots, automated ticket routing, predictive maintenance scheduling, and generally boosting overall operational efficiencies. This area is sometimes termed service ops.
Makes sense. Lots of routine tasks there. But which function has the highest growth rate?
That would be risk management with a projected CAGR of 32.40%. This reflects a fundamental shift happening in how companies approach risk. They're moving away from traditional, static, backward-looking risk management.
Towards using AI for real-time predictive intelligence.
Exactly. Using AI to constantly model and predict potential supply chain disruptions, identify emerging fraud patterns before they cause major losses, predict potential cybersecurity threats or data breaches, all in real time. It's about becoming proactive rather than reactive to risk.
Okay. This deep dive has really laid bare the sheer scale of the investment and competition that's defining this next decade in technology.
Yeah.
The key takeaways seem pretty clear. The market is defined by just explosive growth everywhere you look.
Absolutely explosive.
A relentless drive towards more specialized, more efficient hardware, things like ASICs, NPUs, that crucial high bandwidth memory.
Yep, the hardware is getting very specific.
And underpinning it all is this defining geopolitical conflict, this technological arms race.
And that conflict, as we've seen, is really centered on Huawei's incredibly ambitious strategic attempt to overcome a fundamental deficit in raw silicon manufacturing power by investing, instead, in unprecedented system-level architecture and sheer scale.
Right, through things like the unified Commodore networking technology and those projected Zetaflop PE scale superclusters. They're essentially trying to build the future by sheer force of system engineering and massive scale.
It's a fascinating gamble.
Now, we've focused this entire discussion, really, on the race to build the infrastructure capable of scaling up today's dominant AI models, primarily the large language models that grab all the headlines. But here's the final provocative thought I want to leave you, the listener, with.
Okay.
The next great seismic shift in computation, the thing that could change the game again, is actually already underway in the research labs.
And that shift is likely the convergence of two major, potentially complementary technological fields. Quantum AI.
Quantum computing applied to AI problems.
Exactly. Which promises to revolutionize certain types of incredibly complex optimization and simulation problems, things currently intractable even for classical supercomputers. Think drug discovery, materials science, financial risk modeling.
Okay, quantum AI in the other field.
And physical AI,
Right.
which refers to building sophisticated AI agents, maybe robots or other systems, that are designed not just to process information, but to act intelligently and autonomously in the physical real world, interacting with objects, navigating complex environments.
Right. So, the infrastructure we've detailed today, those absolutely massive Atlas clusters being planned, the hyperscalers' $100 billion data center buildouts, almost all of that is being built and dedicated today to scaling up generative AI and current machine learning approaches.
Correct. That's where the immediate commercial demand lies.
So the critical question, perhaps for the next decade, is this. How will this immense brand new computing power, built at such staggering cost for today's AI, pivot and adapt to meet the fundamentally different processing demands of tomorrow's quantum AI breakthroughs, or the needs of truly widespread physical AI?
That convergence, figuring out how classical Zeta-scale computing interfaces with nascent quantum capabilities, or how it supports potentially billions of physical AI agents, that is where the truly mind-bending innovation is likely to happen next.
And that is definitely what you need to keep watching.